Hi, welcome back. This is the first actual explanation video, so let's get started. It's going to be about logic and sets. As we've already mentioned, that's the best for foundations. So yeah, let's just begin. As the title suggests, we're going to cover two major ideas here. So the first is going to be logic. And in logic, you really have for high school only some operations and some truth tables. So you have operations, and then you also have truth tables for each operation. Tables. So what are the operations that we have? We have not, we have and, we have or, we have if then, and we have the equivalence operation. So this is and this one is also called the implication. And then we have equivalence. So equivalence. Or short form is if with two F's. Okay, so like this, if. Let's just go quickly through each one. So what you actually first need to understand is that in logic we have statements. And what is a statement? Well, a statement is any sentence that can be classified as either true or false. So for example, questions cannot be statements because, well, it's a question. So is the sky blue? That, for example, isn't a statement because we can't say it's true or it's false. The statement would be, for example, the sky is blue or the sky is green. The first example would be correct, so a true statement, and the second example would be incorrect, so a false statement. And equations also count. So for example, if you have 2 plus 2 equals 5, this is also a statement, but it is a false statement. Now, say we have a statement A, and we can just say that A means the sky is blue, okay? The sky is blue. And yeah, let's just make the truth table for each operation. Starting with not, because this one has the highest priority when dealing with it. So we have A and we have not A, so that's how we would write not A. In Boolean algebra, we would also write A with a conjugation symbol at top. So like this. Okay, if A is true, so if the sky is indeed blue, then the statement the sky is not blue, or not the sky is blue, so its negated version, the sky isn't blue, has to be false. And if the statement the sky is blue is false, then the statement the sky isn't blue has to be true. How does it work? If you're in college, there's also the so-called law of excluded middle or law of excluded thirds, and it means that there is no third option, but a special branch of mathematics actually allows a third option. So the statement, so it doesn't have to be either true or false, it can be nothing really, but for high school you don't need to know that. So that's not. Let's move to and. And requires two statements. So let's have a second statement, B, which is the grass is green. Okay, so the grass is green. And you have A, and you have B, and then you have, and the symbol is this. So, not really the asterisk, but the exponentation symbol, A and B. So you have true, true, false, false, and you have true, false, true, false. These are all possible combinations of A and B. So if where A is true both times and B is once true, once false, and when A is false both times and B is true once and false the other time. Now, if both of the statements are true, so for our example, they are indeed true, the statement the sky is blue and the grass is green has to be correct. Now, say that our statement was the grass is pink. Okay. Now we have this example. So the sky is blue and the grass is pink. Is this statement correct? No, it is not, because the grass is not pink. So the truth table here would be false. And same if we switch the order around. And if both of the statements are false, then it would also be incorrect. So it's only correct when both statements, both substatements are correct. In every other case, it is incorrect. Then we have OR. And this is the symbol for OR. Also, in Boolean algebra, AND is actually times, or the multiplication, and OR is the summation, or plus. What does this imply? It implies that AND has a higher priority than OR, and it also implies that, for example, if you have a statement A times B, and one of them is true and false, you use ones and zeros for true and false as well. So if you multiply 1 by 0, you get 0. And if you multiply 0 by 0, you get 0. Or 0 times 1 is also 0. So you see how all of these evaluate to false, just like they do here. The same goes for B1 times 1. Well, this equals 1. So that's why this one, the first example where both statements are true, is also true. Now, what about plus? So for OR, you have A or B. If any one of these is true, then the statement is true. So if you have 1 plus 1, in Boolean algebra, we can't really have 2. So you just get like 1 again, okay? So you have 1, 1, 1, because at least one of them is correct. And you have 1 plus 0 or 0 plus 1, well, in each case you're going to get 1, okay? And then if you have 0 plus 0, well then that's still 0. So that's the truth table for OR. The next one is the so-called implication, or if A then B. Okay, so we have implication, and this is the symbol. So we have A, B, and A implies B. Okay, so this is a bit tricky because we have to look at it as a logical starting point. So A is our logical starting point and B is our conclusion. If we have a true starting point, a correct starting point, so that we didn't break any rules, so we have 1, and we get a correct conclusion, then we can say yes, A does imply B. For example, an implication could be that if a function is differentiable, then it also has to be continuous. So we have that differentiability implies continuity. Since this is the intro to high school, that you probably don't understand these terms yet, but another example would be if 1 is less than 2, then that, or less than 3, and 3 is less than 4, well, this would imply that 1 is less than 4, okay? So that's, for example, that's basically an example, okay? Or one actually more logical one would be, so if we take like geography, okay? If Madrid is the capital of Spain, then that would imply that any other city can't be the capital of Spain, okay? Well, you know, there are also some states that have like multiple capital states, but we won't go into that, okay? Now, if A is true and B is false, then A implying B cannot be correct, because it just doesn't work. If you have something, for example, that, let's say, the sky is blue, and then the grass is pink, well, the sky is indeed blue, but that doesn't imply that the grass is pink, okay? Now the last one is if A is false, or the last two. What happens then? If we have an incorrect starting point, we can prove anything. So from an incorrect starting point, anything you prove is valid. So that's true in both cases. Why does this work? You can kind of imagine it like an innocent until proven guilty approach. So if you have evidence that isn't true, then you can't prove somebody's guilt based on that. Okay? So these have to be still innocent, which is one. The only times where you actually say that it doesn't work is if you have a correct assumption and then prove that that it doesn't imply the other thing. Okay? So for example, if you have an incorrect starting point saying the sky is pink, so that means the grass is yellow. Well, sure, if the sky was pink, that might happen. And one thing is that actually in math or in logic, a lot of these statements make more sense if we look at it in terms of actual equations or statements or theorems. So saying like if a function is, let's say, complex, then it can imply differentiability. But let's say that you can't ever have a complex function. Well then, yeah, sure, it can imply anything. If you break some rules, yeah, you can prove anything using broken rules, so that's why it's always true. Lastly, we have the equivalence, or if, with two f's. As the name suggests, this means that two statements are in fact equivalent, so they describe the same thing. Okay? So if we say a glass half full, that's the same as saying a glass half empty. Yes, you can look at it any other way if you're like in a different way if you're a pessimist or a optimist, but it doesn't really matter. You're still describing a situation where you have a glass and half of the glass is filled with a liquid and half of the glass is filled with air. So if one is true, so if you say the glass is half empty, then the glass also has to be half full. Okay, so this would be true. But say that you have a statement and you say the glass is half empty. But the statement the glass is half full doesn't hold. It's incorrect. Well, then the two statements can be equivalent because if the statements are equivalent, they should be describing the same situation. If I say this desk is black, and then somebody else says, well, this desk is any color except red, white, pink, yellow, blue, etc. And they list every single color except for black. So any other color but, well, that would basically just leave black, then the statements are equivalent. But if there's like an option where they don't describe the exact same situation, they cannot be equivalent. Okay, so in these two cases, they cannot be true. Because if they're describing the same situation, and one of them is true and the other one is false, well, they cannot be describing the same situation. And then lastly, we have if both of them are false, then it's also, they are also equivalent. So that's what it basically means. You can always, for example, say 2 plus 2 is equivalent to 4. This is actually true. So whenever you see 4, you can always replace it with 2 plus 2. And whenever you see 2 plus 2, you can always replace it with 4. So because they are equivalent. Now, what does this mean? If they, for example, weren't equivalent, so 2 plus 2 equals 5, these two cannot be equivalent because you can't replace 5 with 2 plus 2. It just does not work. Okay? So that's how equivalence works. And these are just the 5 operations that we have and their logic statements. For example, if we look at some special cases, like let's say you have not A and B, or C implies D if, let's say A, or let's just replace these again with A and B, so we won't have too many statements. So let's say A implies B not A, okay, like this. So let's say we have such a statement. how do we approach it? Well, we have to basically only compare two statements at a time. So let's just first write the logical options for A and B. We have 1, 1, 0, or 1, 0, and then 0, 0, 1, 0, like this. Okay? Now, we see the first thing you do is write the negations. Okay, so we have not A, and we don't have not B anywhere. So we just have like not A. So what we're going to do is we're just going to compare this and this one here. So that would be 0. If A is 1, then not A is also 0. And for these two, it's going to be 1. Next up, we have, we just go into the innermost, or we go according to the priority. So the innermost parenthesis is going to have the highest priority. So let's say we have B, if and only if not A. Now what we're going to do is we're going to compare the truth tables for not A and for B. And we're going to match them according to this truth table, okay? So if both of them are going to be 1, we're gonna get a 1, or true. And if both of them are false, we're going to get false. Now let's see. Here both of them have varying values, so it's going to be false. In this example, they have matching values, and in this one, they also have matching values, and here they're varying again. So we have 1, 1, 0. Okay, now next up, we have the second innermost parenthesis. So this one, we have A implies the fourth column, if I'm not mistaken. So like this, let me just delete these two, or not apparently. So the innermost column, or the fourth column, we have this one, A implies the fourth column. Now let's look at the values. So we're going to follow this truth table, and we're going to look at the first column for these values, and the second and the fourth column for these values, okay? So 1 and 0, that's, or yeah, let's just write this. A implies B if and only if not A. Okay? So A, we have 1 and 0. That's false. So we said we have a correct starting point, and we proved that it doesn't imply the following statement, so that's why it's incorrect. Now let's move on to the next one. We have 1 and 1, that's going to be equal to 1. And then we have two incorrect starting points, so it doesn't matter what values B, the fourth column takes on, they're both going to be correct. Okay. Next up, we can either have not A and B, or we can have here B or this one. And we mentioned that and has a higher priority. So it actually means that we have parentheses like this. Okay? So you have not A and B. Not A and B. And we just look at the two columns to find the matching values. So we have here, we have not A and B, or B here, okay? And we're looking for where they both are equal to 1. So that's only going to be in the third case, and the rest of them are going to be false. Lastly, we just look at this one or this one. So we look at the last two columns and see where both of them are true, or where at least one of them is true. So right here, you can just write X. Some teachers allow this, that you write X and that represents the whole thing, some don't. We're just going to use it here because it's quicker. So not A and B, here both of them are 0, so it's going to be false. And here, the first column has ones, so it's always going to be true. So we get that our statement is false if A and B are both true, and true in every other example. Okay? And the procedure is just basically follow the order of priorities. So, and you have just the innermost parenthesis, then the outermost parenthesis, and you go one operation at a time. So you don't take more than one operation. You wouldn't take A, B, and then B if and only if not A. You would first take not A, and then just compare not A and B. Okay? So that's how this one would work, for example. And another thing worthy to note is that if, for example, you get X, and you have 1, 1, 1, 1, so only true values, then you have what's called a tautology. So that's a statement that is correct regardless of the input or the initial values. That's another thing worthy to note. And interesting thing, you learned that in college, is that if a statement is a tautology, it has a proof. And if it has a proof, it is a tautology. So it's having a truth table that's a tautology is equivalent to having a proof. Okay? And yeah, that's basically the logic part covered. And now we can just move on to sets. Okay? So sets. Similar to logic, you also have some operations, but we first need to define a couple of things as well. First, what is a set? A set is basically a container. So it stores elements. You have A equals a curly brace, and then you can either list all of its elements, so for example 1, 2, 3, or what you can do is you can list or give the rule for how to find these elements. So you can say a natural number that is less than 4. Okay, so that would be the same thing. Generally speaking, you use the first approach when you have 2 to 3 elements or 1 to 3 elements, so very few. And you use the second approach when you have more elements, and you can also have infinite elements in a container or a set, so that's why this approach, the second approach, this one, is a bit more practical. Now, say that we have to mention two special sets first. So the first one is the universal set, which contains every element that we're interested in right now. So you have a general universal set which contains literally everything. But for example, you might look at a case where you have 5 elements of interest. So 1, 2, 3, 4, 5, for example. Then the universal set would contain 1, 2, 3, 4, and 5. Okay? Now you have also the empty set, written like this. And it means that it's empty, it doesn't have any elements. So it's the set that contains no elements. So for example, you could say A is the empty set. Okay? You can also write A equals, and then just empty curly braces. Okay? You can also write that. And generally speaking, though, this approach is preferred. Now, if we were to cover... Now, next up, since we have elements, we must also tell how an element belongs or relates to a set. So, for example, we have the operation belongs, which is like the euro sign but without the 2 lines here. And this means A is an element of the set B. Or, for example, in our case, we could say 1 is an element of U, because we have 1 here. And one thing to note is that you can have recurring elements in a set and it doesn't change the fact. So for example, 1, 2, 2, the set 1, 2, 2 is the same as the set 1, 2. It doesn't matter. You can have infinite 2s. We just look at if it contains the same elements, not if it contains the same amount of occurrences of the same element, okay? Of same elements, okay? So that's basically another thing you should probably know. Now we can get into the actual operations. So we have a set A, and we can have a set B. And you can have their union, so that would kind of be like a plus in Boolean algebra, or literally. And the sign for the union is this U. So that means A union B. Let's say A has 1 and 2, and B has 2 and 3. And then A union B is defined as A, where A belongs to either the set, or let's say X, so it won't be so confusing, X belongs to A, or X belongs to B. So any element that is either an element of A or an element of B. So let's write it. A union B would then be 1, because if we see 1 belongs to A. So that's good. We have 1. Next we have 2. So 2 also belongs to A. It also belongs to B, but we know it doesn't really matter, because it would be true in either case. So 2. 3. Well, 3 doesn't belong to A, but 3 does belong to B. So this part is true, so we have it here. And then, for example, 4 wouldn't be in this set. Okay? So 4 isn't in A, and 4 isn't in B. So we have 0 or 0, and that's 0. Okay? So 4 wouldn't be here. So that's the union operation. Now we have the intersection. So A intersection B. This one is defined as quite similarly to the first one, except the difference is we use and instead of or. So you have X belongs to A, and X belongs to B. So basically all of their common elements. And we can see that the only common element is 2, which equals 2. Okay? That would be the intersection. We also have the difference. So A minus B, basically. This is the symbol for difference. And you have X belongs, so we have X. X is an element of A, and X is not an element of B. In our case, if we see 1 is an element of A, and it's not an element of B, but 2 is an element of A and an element of B, so 2 wouldn't be right. So that would be just 1. So that's the difference. Lastly, we have the so-called complement. So A complement, and you have X, where X belongs to the universal set, and X does not belong to A. So basically, all of the elements that we're interested in that aren't in A. And why is it called the complement? Because if we have A union, A complement, we will get the universal set. Okay, so exactly the universal set. That's because they complement each other. What one has, the other doesn't. Or what one lacks, the other has. Okay, so that's why it's called the complement. And lastly, you also have the A intersection, A complement, and that's the empty set. So they have no common elements. And these are basically all of the operations that you need to know about here. Okay, so these were sets. Now, sets are a bit interesting because these operations that we defined here, they actually form Boolean algebra. Okay, so you can see that not is basically the complement, and is basically the intersection, or is basically the union, And one thing that you can note is that you can replace any operation. If two things have the same truth table, then they're equivalent, okay? So instead of the implication, what you can do is you can write not A or B, I think. It's like this. So if we look at the truth table, A, B, not A or B, and just look at 1, 1, 0, 0, 0, 1, 0, 0, 0, 1, 1, and then compare them. We have 1, 0, 1, 1. Yeah. So you can, instead of writing the implication, you can write its equivalent statement, which is not A or B. And you can see that basically you can form any of these with just any of these implications or equivalences with just not and basically. Yeah, I think you can also have or yeah. So basically they not and or are sufficient to cover basically any operation. So yeah, that's how it basically works. And sets, I think I also covered everything you need to know really. There's one minor thing that you might need to know, and that's the so-called De Morgan's laws. So you have the Morgan's laws, and that's basically how a negation affects an conjunction or disjunction. So yeah, and can also be called a conjunction, and or can be called a disjunction. Okay, so say you have not A and B, that's equivalent to not A or not B. And if you have not A or B, that's equivalent to not A and not B. Okay? These are the De Morgan's laws. So what you can do is, instead of just using truth tables to prove things or find the values, you can also just sometimes use this Boolean algebra, but generally speaking we're allowed to use truth tables. So that's why we're not focusing too much on actual Boolean arithmetic. And yeah, that's pretty much all you need to know, and I hope you enjoyed this first video, so I will see you in the next one. Okay, sorry, so a quick thing I did forget to mention is the so-called subset. So you also have a special operation, which is denoted like this, and it means, or you can also write it just like this, almost like a C or like a U rotated by, what, 90 degrees to the right. And then sometimes you have this bottom line as well. Generally speaking, if you have a proper subset, you have this one, and if you have what's called not a proper subset, you have this one. So what does it mean? Well, if A is a subset of B, it means that every element in A is also in B. So for example, you have A is 1, 2, and B is 1, 2, and 3. Then A is a subset of B because every element in A is also an element in B. And if we have this line, it can also mean some teachers or professors allow that they are interchangeable. For example, our analysis teacher in college, she uses them interchangeably, or she uses this one but doesn't mean strictly, like she uses it even if despite it not being equal, for example. Okay, so if for example A, 1, 2, and 3, if they're the same, so if A is a subset of B and B is a subset of A, then A is equal to B. That's basically how you define if two sets are equal to one another. And yeah, that's basically the subset operation, and I think that's pretty much everything you need to know. So, oh yeah, one thing, we have a so-called proper subset. So that would be that it's actually a subset. So our initial example where A was like 1 and B was 1 and 2. I know it was 1, 2 and 1, 2, 3, but for the sake of speed, let's just write them like this. So 1 and 1, 2. A is a proper subset because it has less elements, so it's not the same as B. And it has elements, so it's not it's not empty, okay? So that's what you need to know. These would be improper subsets. Like, they are subsets, but they're not a proper subset because an empty set is basically a subset of every set, and if you have two sets that are equal, they're not really a subset. So that's why we have the term proper subset. And that's pretty much everything we needed to cover. So yeah, I'll see you in the next video.